So now we are in segment 6 of module 2, and we are going to talk about the problem of randomized selection. A special case of it is the problem of finding median in an array of numbers. So what we will do is we will present a recursive algorithm to find the kth smallest element in an array of n numbers, and this is going to be, of course, a randomized algorithm. And chances are that you have seen a deterministic algorithm for this problem. And if you recall that the deterministic algorithm is probably not a very trivial algorithm. It is somewhat complicated, but the algorithm that we are going to present today is very simple and elegant. Okay? And we will exercise our understanding of conditional expectation to analyze this algorithm. The reference for this algorithm is Dasgupta, Papadimitriou, Vazirani. It is the basic book on algorithms, but they do not have a complete analysis. So you have to pay attention to the analysis here. So let us just formally define the problem. Your input is an arbitrarily ordered array of n numbers. Okay? Repetitions are okay. It is arbitrarily ordered. Of course, if it is sorted, then it will be easy to solve this problem. So it is an arbitrarily ordered array of numbers, and you are given an input parameter k. And what are you asked to find out? You are required to find the kth smallest element in the array S. Okay? Of course, when k is n over 2, you get the median. And importantly, we want this algorithm to be simple, because we already know a complicated algorithm for it. Okay? So without further ado, just let me make sure, is the problem clear to everybody? Okay. So let us proceed to understanding the algorithm. It is basically recursive, so we are going to call this high level function call select, and the inputs will be the array S and the parameter k. Okay. So here is where the randomness comes up. So we start by picking a number uniformly at random from the set S. So it is basically some element in this array. Okay. And we look at that value v, and we use that to partition S into 3 subarrays. Okay. This is a very intuitive algorithm, you think about it. So whenever, so you basically run a for loop through the entire list of elements in S, and for each element that is less than v, you include it in this the first subarray S left, if you will. And whenever the number you encounter is greater than v, you include it in S right arrow, if you will. Okay. And whenever you will, because of duplications, you could have numbers that equal v, which you just put them into S down arrow. Okay. So you get 3 sublists. So here is an example, quick example. So let us say this is the array that you have. You pick a random element within the array, and what do? All those numbers that are less than 9, you put them in the left array. You have 3 9s, so you put them in the S down array, and then there is one element greater than 9, so you put that in the S right array. Let us actually look at this. Suppose you want to find the third element in this array. Which sublist will you look into? Clearly, you will look into S left. Okay. If you on the other hand were to look at if you were looking for the 8th element in the array, okay, there are 10 elements in this, if I guess. So 8th, you intuitively know that you only have to look at the S down, okay, and so on. So the moment you break it up into these sort of sublists, you know where to recurse into. Okay. So that is exactly what we are doing here. If the input parameter k is less than the cardinality of the left subarray, then we know that it's going to be somewhere in this subarray. So we basically just invoke select S left and use the parameter k. Otherwise, we check if the k that we are looking for is greater than the cardinality of this array plus the cardinality of this array. Okay. If it is greater than these two cardinalities, then we must be looking at, so they are not going to, the kth smallest element is not going to fall in the first two subarrays, it is going to be in the third subarray. Okay. So, that is why we will recurse into the third subarray, but we need to be a bit careful here. So, what will the parameter be over here? K minus, yes. So, you will have to do k minus the cardinality of S sub is that it? Yeah. Yeah. Okay. So, so that is going to be our new parameter, and otherwise what is the option that we have? If it is not going to be recursing into the left array or the right array, you are left with the middle array, but all the elements in the middle array are just the element v. So, we simply return v. Okay. It is a very intuitive, simple algorithm. So, any questions? Oh, where?
Step 3, should we select S left array K minus
No.
this step 4?
In step 4, the cardinalities should be subtract.
It should be K minus S left minus S.
Okay. Yeah. Sorry. Yeah. Thank you. Yeah. Okay. So, other than that, is the algorithm clear to everybody? Let us now analyze this algorithm. We're going to see that the running time of this algorithm actually is O of n on expectation. Let's try to understand why that's the case. Let's use Li to denote the number of elements in the ith recursive call. We start with n elements, so let's start with L0, and L0 is n. Notice that the time spent in the ith recursive call is proportional to Li. So we might do other things, but essentially what we do in the ith iteration is, or the ith recursive call is we sweep through the list of elements that we are focusing on and try to understand which ones are less than the pivot element and which ones are greater than the pivot element. So it requires that one sweep, and therefore the time spent in the ith recursive call is proportional to the size of the subarray that is focused on. Okay, so now let's make a claim. What we claim is that the expected size of the array at iteration I, that's Li, given that in the size of the array in the previous iteration was some fixed L sub I minus 1. Now, given that was the size of the array in the previous recursive call, what is the expected size of the array in the current recursive call? We claim that that's going to be a fraction of the previous size, so a fraction 7 over 8. Okay, let's try to understand why that's the case. Let's look at the pivot that we chose. That's pivot B. If we are lucky, that pivot is going to fall between the 25th and the 75th percentiles. And clearly the probability of being lucky is 1/2. Okay, so how do these ideas play out? Well, let's try to be a little bit more careful about this. What we care to bound is this expectation on Li given this condition. And let's look at how that can be worked out. Well, as we noted, if we're lucky, the size of the array is going to shrink. Otherwise, we could be unlucky, and it's hard to figure out exactly what it's going to be. But since we are just interested in an upper bound, we can just use
we can just assume that there is no shrink in the size of the array at all. Okay. But now here, the being lucky and unlucky happen with probabilities half and half. Now you may ask, why do we claim that the size of the array shrinks to 3/4 the previous size when we are lucky? Well, to understand this, you should realize that the two extremes are within the lucky region is the 25th percentile and the 75th percentile. So let's look at these two extremes. They happen to be symmetric. So let's just focus on what happens if the element we choose, the pivot element is the 25th element. Now that's going to divide up the array into a quarter of the array and the remaining 3/4 of the array, and the median we will be able to figure out is in the larger of those two, which is 3/4 of the array. And therefore the shrink in the size of the array is a factor of 3/4 at least, provided we get lucky. And that's exactly why we have this 3/4 over here. And when you evaluate this expression, you get 7/8 times Li minus 1. Now we want to bound this expectation of Li. And we know that the expectation of this Li is nothing but the expectation of the expected expectation of Li conditioned on Li minus 1. Okay, and keep in mind that we already have a handle on this conditional expectation inside, and that's going to be 7/8 times Li minus 1. We worked it out for a specific value, but for any random variable also, it's going to be 7/8 times Li minus 1. And by linearity of expectation, you get the 7/8 outside, and so expectation of Li is 7/8 times expectation of Li minus 1. And you can continue this recursively, and as a result, we would get expectation of Li to be 7/8 raised to the power I times n, because when the recursion ends at L0, you will just have n over there. Okay, so how does this impact the running time? We claim that the expected running time is O of n, and let's see why that's the case. Let's just denote the running time as t. Now, if you recall, I said that the running time in each recursive call is proportional to the number of elements that we consider. So let R capture that proportionality, so R is some constant. So the running time t is at most R times the number of elements that were there in the 0th recursive call, the first recursive call, and so on and so forth. Okay, and if t is that value, then the expectation of t by linearity of expectation and just taking the expectation into the expression, you'll get R times expectation of L0 plus expectation of L1 plus expectation of L2 and so on. Okay, and we've already derived a value for the expectation of Li, so we can plug that value into this expression, and what we will get is the sum of a geometric series, which is not hard to evaluate, and we'll get a value of an upper bound of 8Rn for the expected running time, which of course, because R and 8 are both constants, this upper bound is O of n.
So let's conclude this segment. We introduced the case selection problem, which is a generalization of the median problem. Provided a very simple randomized algorithm. Okay, we analyzed its running time, and we showed that it runs on expectation in O of n time. But there is one question that I want you to ask yourself. So this is an expected time running time analysis. How can you trust this answer? So can you be sure that it won't take too much time in the worst case? Okay, what does that even mean? Okay, so these are some questions that we need to ask ourselves, because when you claim something on expectation, you're not guaranteed to end in O of n time. There could be situations where the actual running time could be much higher than n. That's a possibility. Okay, and if you are going to run a mission critical operation in which this shows up as a critical piece, and you need some more better guarantees than this. So, that is something that should rankle you, and hopefully we will be able to address that in a subsequent module. Okay. So, with that we come to the end of this module 2, where we talked about random variables and the expectation of random variables, and we looked at a couple of examples. In the next module, we will be talking about tail bounds, and we will address exactly this question that is hopefully rankling you. We will try to go from expected time analysis, not just go away from it. Expected time analysis is also important, but we will also try to make claims that hold with high probability, so that we have this extra guarantee that with high probability, and we can actually make it arbitrarily high, with high probability the running times will be good enough for us. Okay. So, that will be the focus of the next modules. Actually, not just one module, might spill over into multiple modules. Okay. So, with that we will close module 2. Thank you.